So in this video I thought we'd jump in and take a look at the additions to the code from the previous video to actually put in the a SineWave lookup table. It's fairly straightforward what I did here. Right now I've created a SineWave output here named Sine2. This is coming out on the lower 8 bits of the 16-bit I/O port. On the unit, let's go ahead and take a look at a photo quick of what I've done. So I've prepared a second R2R network board. So we've got the one we built originally, and we've got a second one I've added here. This is the one outputting the triangle wave that we looked at in the previous video. This one will be outputting the sine wave from the ROM. And this one's wired up to just plug into this lower, this is a dual header into those lower set of pins. It's wired the same way, ground, VCC, and the data pins. If we take a quick look at the assignment editor here, we'll see that I've added a Sine2. Let me sort these because it's slightly out of order. There's this Sine2, and this is where we're outputting to that 16-bit port, the 8 bits out onto that port. In the Verilog code, if I can get back to it, the Verilog code, see, I've added that Sine2. It's an output that is 8 bits wide. We've got our register, or our counter register we defined before that we actually do the divide by 2s in. I've added a definition for the SineWave ROM, and this is saying I am 8 data bits wide and I have 256 entries. So in this case, this would be a 256 byte ROM. I'm then doing an initial read mem H. The H says the incoming file is a hex file. Go ahead and look for this file name in the same folder as the source code folder here, and put that into this variable named SineROM that we defined up here. And if we look at the SineWave table, this is just simply a list of hexadecimal values. And of course it'll be 256 rows deep. There's a couple of dead rows down here that don't need to be here, but it's got 256 entries in it. They're hex values. And it starts at an 80 hex, 83, 86, and basically if you follow this pattern it would produce a sine wave. Again, this line of code here is reading the hex values out of that file into this little two-dimensional array, 8 bits wide, 256 positions deep. We assign the LEDs as we did last time. We go ahead and hook up the R2R network to the system. And remember, the definition of this is the pin I want the R2R network to be connected to originally, and then each pin gets defined with a -1, -2, etc. all the way back. We can ignore this entry here. It kind of duplicates the entry down here, and this is where we basically say take that Sine2 output we defined above, and he's going to be set to the data that I find in that SineROM variable based on this address. So R2R is connected here, his 8 positions, to various positions in that divide by 2 counter, the 26-bit wide variable. And this really is just literally saying, go to this ROM table, and from this address, return the data value and assign it there. And we looked at Sine2, and we can see that it's attached to I/O pins on the device. So after taking a look at the code itself, I put together this little block diagram to kind of talk through how the code's structured and a way to think about how the system is operating internally. So the first thing we have is that 26-bit counter that we defined with the reg 25 through 0. And then we've said on the negative edge of the 50 megahertz clock, add a 1 to this. It's 26-bit wide, or 26-bit wide field with the value of 1. So it'll keep adding 1 here. And of course, when this one overflows, it works all the way down. So we've got our slowest clock sitting here with all the divide chain all the way down, up to the fastest. This would end up being 25 megahertz if we looked at this pin here, because there's a 50 megahertz signal coming in, and it's doing a divide by 2. So talk a little bit about the LEDs that are on the board. I simply have got those hooked up to these 4 most significant bits, which gives me the slowest up count, so I just have a visual reference on the board that something's happening. And those LEDs are just connected to counter positions 25 through 22, which is here. And we've discussed before that I've not these because when the bit is a 1, I want the LED lit. So if this bit is a 1, the not here means we're outputting a 0 to the LED, and the LED gets forward biased and it lights up. The other thing I talked about a little bit in the code, and we'll talk about again, is I'm setting this local parameter that is the most significant bit that I want the networks here tied to. In this case, it's bit 11, which is right here. And if we come down and look at the code, we define the bit 11 and we assign it to bit 8, and then -1, -2, -3, and that's how I get this connected across like this. I could change the code here to be 12 and shift these up a bit, or 13 and shift them up 2 bits, etc. So I can move the connection point kind of up and down inside of the counter here, just so I can generate various frequencies on the output. Previously, in the previous video, we looked at the fact that I've got this binary up count essentially happening here, and I'm feeding those directly into that R2R network we looked at in the earlier video that's outputting the triangle wave. And there's this capture here just showing the triangle wave coming out. The additions we made for the sine wave table are this. We created this SineWave ROM with this register 81 256 bytes definition, and then we loaded the SineWave ROM image as a hex file into that variable, and there's kind of the top of that file. So when these are outputting all zeros, the ROM's outputting hex 80. When it's outputting a binary 1, it's outputting 83, etc., etc., etc. This is 256 bytes deep. We then take the output of the ROM, which are these values here, into the R2R network, and that produces the little sine wave here that we've captured here. So I've got the oscilloscope running, looking at the 2 channels. We're here on the web server inside of the oscilloscope, and we can go over to the live screen, and we can see what I'm seeing on the actual screen of the oscilloscope. And as we did in the previous video, we've got the raw binary up count running here with the least significant bit to the most significant bit. And we discussed briefly where when this gets to its maximum value, all of these bits are a 1. On the next count, they all become a 0, and we drop back down towards ground. So we're seeing that same triangle wave we saw last time. If I bring in channel 2, and I turned it off. Bring in channel 2. This is the second R2R network that I built up today that we saw in the photo, and there's the output of the sine wave from it. So we've got the binary up count here going into the ROM. The output of the ROM represents the sine wave here. And if we take a quick peek at, let me find it here. When we're outputting all zeros here, to the addresses of the ROM, we're getting out an 80 hex. And that correlates to, here's the all 0 point, and 80 hex is essentially halfway between 00 hex and FF hex. So when we're outputting a 0, we're outputting this point here, and then as the up count happens, we get our nice sine wave. And you'll notice here that the triangle wave, one cycle of it, is identical to one full cycle of the sine wave. Anyhow, that's really all there is to this. We saw the definitions before in the code, and I've captured it here, of creating the lookup ROM, loading the lookup ROM, wiring the lookup ROM to be connected to this up count. Anyhow, let's jump in and let's go ahead and change the bit that I'm connected here. If we move it to 12, the starting bit and the up counter to 12, we should double the frequency. So let's go ahead and save the project and let that compile. It'll take a second here to compile. Oh, I've just noticed I don't have the USB blaster plugged in. I'll need to plug that in before we program here. Assuming I have an extra USB cable floating around. There doesn't seem to be one laying here on the bench, which is surprising. Oh, we blew up here, expecting N module. And that's because we have a extra character inserted there. So let's go ahead and compile again. And we'll let this compile. And I will dig here while it compiles for a USB cable that we can use. And I've got one right here. It'll be interesting to see what COM port the USB blaster connects on, because I'm going into a different USB port. And I'm also going with the USB blaster through a hub. Check for... Oh, how did I pull that off? Well, another syntax error. I did a bit of cutting and pasting earlier to rearrange things here to make the code seem a little more logical, and I didn't do a test compile. So we fixed that issue, hopefully. We'll let this compile. Let me go ahead and bring up. Well, it still is seeing the USB blaster. That's good. We get our compile status over here as this runs. As you know, this takes a little bit of time. And what I want to do is just come back around once we program it with this, and we'll just jump back straight to the oscilloscope, and we should see that the frequency has doubled, because we're driving it essentially twice as fast. So once these get done here, it's compiled. Let's go ahead and program. And let me bring back the scope while that's programming. And I actually had this exactly backwards. We've moved it up a bit, so it's going to be half the frequency it was before, which is what we're seeing here. Hopefully several of you caught that as I was doing it. Let's go ahead and move it the other way. So we were originally on 11. If we change it to 10, we should now double the frequency. Again, by changing it to 10, actually that's not the image I want. By changing it to 10, we are shifting the connections here down by 1 pin. So the first bit here is not connected here, and the last bit will be connected here. And that's kind of the power of using this local parameter, is it makes it really easy to shuffle this around. Let's come back and compile. And now we should see double the frequency we saw before. And we'll go through a couple more iterations here. We'll take this up to the maximum frequency I can drive it and see what the waveforms look like, and down to the lowest frequency I can drive it, and we'll see what the waveforms look like. Apologies for the compile time, even on a very fast machine. This takes a bit. Of course, the machine's doing other work. I'm running the screen capture on the same machine, etc. So, machine's being worked somewhat heavily. And we're done. For this case, I'll go ahead and bring up the oscilloscope display, and then I'll bring up the programmer as well, if it'll load here. Oh, I did not want to do that. I actually ran a second version of it. So right now we're running on the previous download to it, where we had shifted the bit up to 12. We've now shifted to 10. So I'll go ahead and start the programmer. We'll see the board shut down as it's being programmed. And once the code's there, we'll see the board light back up. And there we are, we've doubled the frequency just by shifting which bits it's connected to up and down. So let's now push it to the limit. So let's kick this all the way up to bit 25. And that should run at the slowest it can run. And we'll go ahead and program that up. I'll compile it first. I don't know if you've noticed or not, on the scope display here, I'm actually measuring the frequency, in this case of the triangle wave, but that's giving us the frequency. It's currently running 24.41 kilohertz. We're still compiling here. Might be a good time for a sip of coffee. The fuel that I run on. I don't want to set that on the desk, or you'll hear me set the cup down. And let's bring back the oscilloscope display and the programmer, and we'll go ahead and download that. Again, the board shuts down while it's being programmed. And we're now on the slowest possible signal generation, so let's slow the scope way down here. We're at 10 milliseconds of division, 100 milliseconds of division. I'll do a single capture here in a second. So there's a single capture. We can see the frequencies all the way down to 744.5 megahertz. That does not seem accurate. That's quite interesting. We're on 200 milliseconds per division. So we can see that to get through a complete cycle is what, 200, 400, 600, 800. It's quite slow. I have no idea. That must be triggering, or I'm below what the system can measure. Anyhow, you can see this is the slowest that we could measure, and we can zoom into this, and we can really now see the staircasing pattern, whereas the bits are changing here. So as this is counting from this value to this value plus 1, we can see the sine wave increment, and you can see the staircasing. And this is, again, the ROM output being fed to the R2R network, and this raw binary count being added to the R2R network. Let's go ahead and shift it now up to the fastest we can drive it, based on what I've got here, back to here. And let's see, we want to start at position 7. And that'll be 7, 6, 5, 4, 3, 2, 1, and 0. And remember, the array runs through 0. So this should drive it the fastest it can be driven. Again, based on the little design I've got here. And again, while it's compiling, we'll just take a look. We've got the one board plugged in down here that's generating the triangle wave, and the second board I built up this morning that's outputting the sine wave. Electrically, they're identical. They are built in a slightly different position on the board because there was no space here to build them the same, but the wiring behind is identical on both of these. So this is getting close to finishing compiling. You may be able to hear the fan in the oscilloscope running there behind us. Let me just get the scope back running, free running. And we'll bring up the programmer and we'll send that code down. And let's expand out the time base and see what we've got. Not getting really good triggering. Let me see if I can find a better trigger point. I had it there for a second. There's a better trigger point. So one of the things that's happened here is the amplitude of the signals has changed, just because we're driving it faster. So we're clocking at about 195 kilohertz, which actually makes sense. Yeah, I believe that makes sense. We can see that the triangle wave, the shape of it has dramatically changed. In this case, there's a very large transition from FF hex here to 00 hex, and that's a large transition. And due to capacitance and inductance, etc., that's just taking time to roll off. Whereas the sine wave actually looks reasonable, and that's because it's small transitions between every step. So remember here at about the center, it's 80 hex, 83 hex, 85 hex. With the smaller transitions here, we're getting essentially better signal fidelity because we don't have these really large changes in output from about 3.3 volts to 0 on a single clock. We can zoom in here, and of course there's a fair amount of noise. We're not seeing the staircasing. Staircasing is bad. We do continue to have this rough transition right here. Let me see if I can, it's on the screen. So this is a point where we are shifting from, and you can actually see it here, from all ones to all zeros. So we're outputting an FF here into all zeros, and that rolls off. In the ROM code, however, that's interesting. So again, it's nonlinear, the output here. It's not as clean as it could be. That should be shifting from, again, that's all ones to all zeros. If we go back and look in the ROM, all ones would be outputting a value of 7D. When it switches to all zeros, that's outputting a value of 80 as it rolls around here. Where's the scope? Wouldn't expect that to be quite that rough. This just may be how this is electrically laid out. I've got no decoupling on anything. It's just a pretty raw little board. Let's see how far we can drive in here. I'm just kind of curious. Far enough that it's basically meaningless. Anyhow, I hope this has made some sense and maybe done somebody a bit of good. I'll throw in my normal disclaimers here again. I'm not a Verilog programmer. I'm learning on the fly as I do this. I was actually surprised that this worked, where I set assign 2 those 8 output pins to the output of the ROM. I guessed that would work, and it did. Based on what I read, I didn't expect that to work. And that's partly because if we go in here to the assignment editor and we go ahead and look for unallocated pins, let me grab all the pins. We're going to see that there's a bunch of pins on the sine ROM. Outputs, the enables and everything. None of these signals are being driven. They're unassigned. And it just kind of surprises me that this works. Because I'm not talking to that ROM array the way I would have thought it had to. I would have thought I would have had to have assigned. Let me sort this so it's a little cleaner. I was just assuming I would have to assign all these signals. So there's the I'm trying to interpret what I'm seeing here. These being named A out 1, 2, 3, 4, 5, 6, 7, A out 0. Why does that name look identical to that name? It's just maybe the way the Verilog is defined. Anyhow, I expected to have to be able to connect to the ROM, hook up the incoming address pins, hook up the data outs, enable the ROM through the enable pins, etc. And I didn't have to do any of that. I just kind of took a leap of faith and thought, well, this construct would make sense to me if the compiler's smart enough to say he wants the data from this address assigned to these pins, and by golly, that worked. Whether this is, it must be, at least true enough Verilog, it actually worked. So it made the implementation here a lot simpler. I know I'm rambling a bit at this point. We'll wrap this up here in a second. Just come back around that block diagram again. We've moved from 11 here, we've shifted these connections all the way down to the bottom 8 pins here, which are counting the fastest. We've pushed this up to the maximum frequency I can get out. We kind of talked this all through a couple of times here. So anyhow, I hope this makes some sense, and as I said earlier, maybe it's useful for somebody. It was for me to learn. Anyhow, we'll talk soon. Bye.